A few moments later.
Today's video is going to build very heavily on what I've done in the previous two videos about this jet engine. So if you haven't seen those, click here. But if you have seen those, good for you because it's good quality content. Holy shit. My post about my last jet engine blew up on Reddit. Well, blew up's not the kind of term we like to use around jet engines, but it was successful. There were quite a lot of comments on Reddit about my last video, and what I'm going to do is I'm going to make improvements to my jet engine based mainly on what you said. I think one of the most helpful Redditors was Front Cow, and the advice that they said that I should work on the stoichiometry, because they're right, I should work on the stoichiometry. The stoichiometry, if you don't know what that is, it's the balance of the fuel to oxidizer ratio. So if you get it just right, the fuel combusts perfectly with the oxygen, and that will give you higher efficiency. This is along the same lines as what Atensys wrote, and I'm going to follow exactly what they said. I'm going to create a way of adjusting the fuel flow rate proportionally with the motor speed. The first thing I'm going to do is make a new air intake so I can get more air flowing through the engine so I can increase the power. So I'm working on a new air intake for this jet engine, but the airflow out of this is almost nothing. The reason why this is because instead of the air flowing horizontally out the back, the propeller here pushes it to the edges. So there's a higher pressure region round the edge of the bottle, but not in the bit where I want the air to come out of. So I'm switching to this, more like a centrifugal pump. The air intake is going to be at the side, and this increases the airflow rate massively. The airflow out of this thing is actually too powerful, so I've just added a valve to help limit the flow. To achieve stoichiometric combustion in my jet engine, I need to find the amount of oxygen that's flowing into the engine to begin with. So I've created a setup to do this. The setup I'm about to use to measure the oxygen flow rate out of the motor is, well, it's going to make a lot of civil engineers excited.
When a force is applied to the end of a beam, it rotates, and this end rotation is proportional in some way to the force applied. So, using the beam analysis here, I've determined the force required, and then using the steady flow momentum equation, I can then determine the amount of oxygen that flows through the nozzle. By looking at the complete combustion equation of propane with oxygen, I can then determine the amount of propane that needs to be supplied to the amount of oxygen given. Let's test the theory. By drawing some lines on this image, I can determine the angle that the end of the beam has rotated. It's about 30 degrees, which is pi over 6 radians. Plugging that into the equation, that gives about 0.6 grams per second of oxygen supplied.
Now I know how much oxygen the motor can supply. I need to write some code so that I can link that to a servo that will open the valve of the fuel so that I can achieve the stoichiometric ratio.
This is my automatic fuel control setup. So this servo here will control the valve that limits the flow of fuel, and the Arduino acts as a link so that both the air intake motor and the servo can be controlled by the same transmitter signal. In that test, the servo didn't rotate the full 180 degrees that it's supposed to, so I'm going into the code to try and fix it. Fixed it.
This engine's pretty good, and it's more stable than the previous one, but it's still not as stable as I'd like it, and it's not throttleable, really. What I'm going to do is I'm going to convert the steel pipe into the combustion chamber, and then stick a nozzle on the end of that, to hopefully increase the thrust and efficiency. To compare the performances between the old nozzle and the new nozzle, I'm going to use the SolidWorks fluid simulation.
The red regions in this diagram represent high velocity flow, and the blue regions represent static. The average exit velocity for the old nozzle is about 350 meters per second. The new nozzle design is far more efficient at converting thermal energy into kinetic energy, as the maximum velocity here is in the 700 meters per second range. This is the nozzle I'm going to attach to my jet engine. Notice that there's a washer inside, but the washer is made by me. It's made out of a tin can because I couldn't be bothered to order one of the right size, so I just made one. Sticking this on is going to be a lot harder because this is not the same width as the pipe I'm trying to put it on.
I have no way of welding the nozzle onto the end of the pipe, so I'm going to have to come up with something innovative to fix this.
This is essentially just flour, water and salt mixed to make a glue, but this glue should harden when it burns to make a stronger seal. Oh, that's grim. That is actually so grim. I think I've left this mixture long enough to dry, so the engine's ready to fire. The major problem that I see is that I can't cool it with water because the dough will dissolve and it will become kind of a paste again. There were some fumes coming off the jet engine last time I fired it, so this time I'm going to wear a mask for safety. This is a demonstration that even when a flame isn't visible, the exhaust gases are burning hot and can light paper. I think it should be pointed out that this nozzle started off copper coloured, and now it's black. It's oxidized so hard. The copper is oxidized into copper oxide, which is black. Then you look at the rest of it. The doughy bread mixture is completely burnt, but it held, so prove that worked. The rest of it's fine. The motor and ESC are incredibly hot, because obviously they've been working for like 15 minutes straight to do this. And the gas can, it's quite hard to see this, but it's covered in moisture. It's so cold that water was condensing on it.
This engine doesn't look as impressive as the previous one, because the flame is almost invisible. But that's actually a good thing, because the less visible the flame is, the hotter it is, and the hotter it is, the more efficiently it's been combusting, so I think that's a good thing. Whether you're an engineer, a chemist, or just some random person who found this video on the internet, I think we can all agree that colourful, pretty flames are amazing. So I'm going to finish this video off by filming my jet engine at night to hopefully capture the flames in action.
I've just finished firing the jet engine at night, and it's safe to say that this engine will never run again. Almost all of the components are melted, overheated, burnt, I don't know, just ruined. For example, this is the fuel intake. The PVC piping has contracted, and yes, I could replace this, but lots of the other components have also been ruined. Upon later inspection of the engine, the copper nozzle has actually welded onto the brass fitting. It's quite hard to see, but if you look along this line here, there's actually a very small weld joint, and it's impossible for me to make it break apart.